Today we'll discuss about chemical kinetics, the next chapter. Uh, so what do we mean by kinetics? So, uh, chemical kinetics. Kinetics simply means something in motion. In physics we call it dynamics. Uh, so the reaction, all the reactions that are taking place are in motion. Suppose A reacting with B gives us C. So that means the atoms or ions inside the reaction are in motion. And why chemical kinetics? Why to study kinetics? Simply because simply to understand how fast or slow things are moving during a reaction. Suppose we know that from a thermodynamic point of view, the change in Gibbs energy is the change in Gibbs energy of the products minus Gibbs energy of the reactants. So that means the reactants end up as products, and we know that the complexion of the chemical composition changes even in terms of appearance or reactivity. It is different from the reactants, the products that we get. But suppose we know that from thermodynamics point of view, we can say that suppose suppose carbon can form graphite, carbon can also form diamond. But the change, the Gibbs energy change, the standard Gibbs energy change of graphite formation is around 2400 kilojoules per mole, and that of diamond Gibbs energy change or formation is negative 2900 kilojoules per mole. So they are both spontaneous, but one has a negative value, the other one has a positive value, and the question is how long? How long does it take to get to the product? So in this chapter, we'll be focusing on how fast are reactants consumed. How fast are reactants consumed, and so products formed. Products are formed. How fast? And what are the factors? What factors determine or affects that process? And that process is called our rate of the reaction. We'll discuss it. And then how does the reaction proceed? How does the reaction proceed? Now, sometimes we'll end up with some reactions having equilibrium conditions, even though the atoms or the ions are in motion within the, the reaction, but we shall see that sometimes we have equilibrium conditions where the forward reaction and the backward reaction is equal. So to understand this, to understand those topics, we need to focus on something called rate laws and rate constants. These are experiments done, experimental methods to determine the rate law. There are different determine the rate law. Then we have chemical kinetics theories, different theories. We have different theories like the collision theory, and then we have the transition state theory. Then, of course, we have the effect of temperature on reactions described through Arrhenius theory, but it's being omitted, so we won't discuss it. So these are the things that we'll discuss under this chapter. Now, to start with, suppose there are two reactants giving us a product. So how do we determine? Suppose A reacts with B, giving us C. How do we determine its rate? So the determine how fast or how slow. So that is our rate. How fast or how slow things are changing. That's our rate. So the rate of a reaction for this particular reaction would be the change in the concentration C over change over time taken. That will give us the average rate. Let's say the average rate of this particular reaction. So suppose in a graph, suppose we have the concentrations here, that is A plus B, and then here we have the time. Now suppose we have the initial concentration, and then once the time starts moving, the concentration decreases to give us C, our product. So this rate or change is the slope of this graph, and it's a downward slope, so the rate will be given by negative del C, change in the concentration, because since it is decreasing, we're giving it as a negative, change in time. And this one is our average or rate of a reaction. That is how we determine the rate of a reaction. But suppose we want to know at one point, suppose at time t1, we want to know how much concentration has been consumed at t1. So that is called our instantaneous rate of that reaction, instantaneous rate. And for that, we use a differential d by dt of C. So that will give us instantaneous rate for this particular reaction at that point of time. So let's take an example of a reaction. Suppose nitrogen and hydrogen reacts to give us ammonia. So this particular reaction, how do we determine the rate? So the rate of reaction would be the disappearance of nitrogen and hydrogen, or the appearance of ammonia. That's how we determine the rate. So rate of a reaction, rate of this particular reaction will be equal to negative d over dt of nitrogen, or again negative d over dt of our hydrogen, or d over dt of ammonia. Notice that we have these two negative signs because these two are disappearing, these two are decreasing from the initial concentration, and then we are getting ammonia. So here we have a positive sign. So the original rate of the reaction, the total rate of reaction, and notice that here we have 1 mole of nitrogen reacting with 3 moles of hydrogen, giving us 2 moles of ammonia. So our rate of reaction or the total rate of reaction would be negative d over gt of ammonia equal to 1/3, because 3 moles of hydrogen is reacting, negative 1/3 of d over gt of hydrogen equal to d over gt of, 2 moles of ammonia, or half of ammonia, ammonia. So that is how we determine the rates of a particular reaction. So, now let's move on to factors affecting the rate of this type of different reactions. What are the factors? So if you think about factors affecting a chemical reaction, number one would be our concentration. Concentration of the reactants. If there are the concentration of a particular reactant may hamper a chemical reaction or may enhance the formation of the products. So concentration is really vital. Our second point is temperature. Temperature plays a big role. Sometimes because, as we know from thermodynamics, we have exothermic and endothermic reaction. Depending on the temperature, the kinetics of different reactions are different depending on the temperature. Our third point is our nature of the products and reactants. Or for nature of the products and reactants, it's similar to our concentration. Next one is catalyst. Now you know the purpose of a catalyst, why we use catalyst. Catalyst, it enhances the rate of a reaction, it speeds up the rate of a reaction without affecting the final product. It doesn't react with the reactants, but it enhances, it speeds up the reaction. So catalyst, sometimes of course negative catalyst, it slows down the reaction as well. We have the pH of solution or of the reactants, pH of solution. So if it is depending on the reactants, maybe sometimes some reactions are better off with acidic condition, or some are in basic condition. So pH is also important. Pressure is also an important point. Pressure. You have learned from the equilibrium chapter about the application of pressure. If you apply pressure on one side, how the equilibrium gets shifted. So I'm talking about the Le Chatelier's principle, and then of course so these factors are also listed in your book. So I suggest you go through. So we'll move on to our rate law, or sometimes called as integrated rate law. But yeah, we'll go to integrated rate law, or dependence of rate of dependence of rate on concentration of reactants. How concentration affects the rate of a reaction. And we know that the rate from here, it's directly proportional to the rate of the reaction is directly proportional to concentration of the reactants to the power of order. Now, this order is really important. Well, when we talked about that reaction of nitrogen and hydrogen giving us ammonia, so the rate of the reaction equal to the concentration of nitrogen and hydrogen, but raised to the power 3. So this is our rate of the reaction. Now that gives us the rate of the reaction, yeah. So simply put, if there is a reaction as the reactants B gives us products C plus DD, then the rate is directly proportional to the concentration of A over the order and B to the power P, or sorry, X, Y, let's say X, Y. So where X and Y are not equal to A and B. It's not equal to the moles. So our rate would be, if we change the proportionality sign, then we put a proportionality constant, it remains the same. Y. So that is our change, and our change in the rate would be equal to this term. So this is our rate equation, change in rate. Now let's move on to order of a reaction. So order of a reaction, so we know that rate is given by K into A to the power X, B to the power Y. So order of this particular reaction would be the sum of these parts, X plus Y. So this would be our order of this particular reaction. So suppose for zero order, A plus B giving us C plus D. So in the rate A and B to the power 0 will give us rate K. So in zero order reaction, rate is directly proportional to the proportionality constant K. But for first order, suppose first order reaction, and this one, most of the reaction, especially radioactive decay, follows this first order. So suppose if the rate is given by K into A to the power 1 and B to the power 0, then the rate would be K A. So that is our order of reaction. So example nitrous oxide dissolving became nitrogen dioxide and oxygen. So the formation of the product is determined by this concentration N2O5. So if we write the rate will be K into N2O5 and it has the power 1. So the order of reaction is 1 for this particular reaction. Yeah. Now, like for example, second order, suppose let's take the example of a second order. Of course, we'll focus only on the zero order and the first order, but to highlight the example, hydrogen iodide decomposing to hydrogen gas and iodine gas. So, see, rate for this particular reaction would be K into the concentration of hydrogen iodide and square. So, because the 2 moles of hydrogen iodide are decomposing. So for this particular reaction, the order is 2, or it's second order reaction, so on. So in the next video, we'll discuss about the integrated rate law.